Hello, and welcome to this Vivado Quick Take, where we'll be discussing how to use the Vivado Device Programmer to create and program a configuration memory device. Today you will learn how to set the correct bitstream properties for generating a configuration memory device. This is particularly important to ensure that the final bitstream is generated correctly. Once a good bitstream is generated, we will walk through the process of generating a configuration memory device file. We will then use this file to program the configuration memory device on your board. For today's demonstration, we will be using the KC705 board. After we have programmed the configuration memory, the final step is to boot the FPGA from the configuration memory. Once we've gone through these steps, we will have successfully managed to indirectly program an FPGA. This quick take video assumes that you're familiar with setting and editing device properties. We will not be diving into the details of how to do this, so please review the Setting and Editing Device Properties Quick Take video prior to viewing this quick take. We will start with a quick introduction of the new capability in Vivado Device Programmer. We will then look at how you set the correct properties for an SPI-based configuration memory device. We will also examine how to do the same for a BPI-based configuration memory device. Then, we will create a configuration memory file for each type of memory. After we have the correct memory file, we shall use it to program the configuration memory device that is available on the KC705 board. Finally, we'll ensure that we can boot the FPGA from this device. Vivado 2014.1 offers the capability to be able to indirectly configure an FPGA using a configuration memory device. Vivado also offers the opportunity to do this directly via JTAG as well, although that is beyond the scope of this quick take. Configuration memory devices are also commonly known as flash and PROMs. The majority of the configuration memory devices are flash-based nowadays, and the term PROM is more of a legacy usage. Let's take a look now at how we go about setting the correct properties for generating correct bit streams. We'll open up the Edit Device Properties dialog and look for SPI settings under Configuration. The default tool behavior is to leave the SPI bus width as none. This means you have to enter the correct bus width here. In this example, we'll set it to x1, so change the value of the bus width to 1. In addition to setting the bus width, it is also required to set the configuration mode to the correct setting. Since we're using SPIX1, we'll select the setting of Master SPIX1 from the Configuration Mode selection in the left pane of the dialog. Now we can save and close and run implementation and bitstream generation. Let's take a look now at how I go about setting the correct properties for generating correct bitstreams. We'll open up the Edit Device Properties dialog and look for BPI settings under Configuration. In this example, we can leave the BPI settings as default, although note that based on the configuration memory you have on your board, you'd need to adjust these settings accordingly. The example here is based on a BPI configuration memory on the KC705 board. It is required to set the configuration mode to the correct setting. Since we're using BPI X16, we'll select the setting of Master BPI Up X16 from the configuration mode selection on the left pane of the dialog. Now we can save and close, run implementation and bitstream generation. Now that we've generated a bitstream, we can use this bitstream to generate a configuration memory file. The command we'll use to generate the configuration memory file is write_cfg_mem. Usage of this command is documented in the Vivado Design Suite Tickle command reference guide. Let's examine some of the key options for this command. First, format. You can specify if you want MCS, BIN, or hex file using this operation. Interface. This is the type of interface that is used by your configuration memory. Note if byte swapping is required for the given interface, this command will take care of that automatically for you. Size is the size in megabits for your configuration memory. In load bit, this option tells the command that you want to load a bit file at a given address. You can specify if you want to go up or down from the address you specified in the name of the bit file. And finally, the file, which is the name of the output file for your configuration memory. For the SPI configuration memory, the command we would run is this. Note that the bit file must have the correct configuration mode selected to align with the interface here. For the BPI configuration memory, the command we would run is this. Now that we have the MCS file we need, we can open up the hardware manager to configure the memory device. The first step is to add the configuration memory device we have on your board. We'll select FPGA, right-click, and select Add Configuration Memory Device. Then we'll pick the correct part to align with what is on your board. Next, we'll program this part with the MCS file we created earlier using write-cfg-mem, or write-config-mem. Now that we have successfully programmed the part, we'll try to boot the FPGA with the configuration memory. This will ensure that configuration memory has been programmed correctly. We can do this by right-clicking on the FPGA and selecting Boot Device. Before we take a look at the demonstration, let's take a quick look at the hardware we will be working on today. The board we will use is the KC707 from Xilinx. The most important component for this quick take is the BPI Micron PC28F00AP30 device and the Kintex 7 325T FPGA device. Pay attention to the configuration mode setting dip switches, as we need to ensure that these are correctly set. The KC705 board has multiple configuration mode capabilities. We will focus on the setting of the master BPI X16 for this demonstration. Let's make sure that the dip switch setting is set to 010 before we turn on the board. Please refer to the KC705 evaluation board for Kintex 7 FPGA user guide for more details on how to do this. Now let's take a look at a demonstration of indirectly programming an FPGA. In this demonstration, I'm going to reprogram a BPI configuration memory that is available on the KC705 demo board. I've already set the correct dip switch settings to ensure that it is put in the master BPI mode. I have a simple counter design here that I have run through the synthesis phase. I'm now going to Tools, Edit Device Properties to set the correct bitstream properties. We need to search for BPI settings, so I will type BPI in the search box. In the configuration selection, I'll leave the default as is required for the configuration memory on this board. Now I'll go to the configuration modes selection and scroll down until we find master BPI up X16, and we need to ensure that this mode is selected. It'll be highlighted in yellow when it's selected, and we can hit OK to close the dialog. Now I'll click on Save Constraints and click on OK for the next dialog that pops. Now we need to ensure that we have a DRC clean design. So let's check on Report DRC and run the default rule deck and confirm that there are no violations. So now we're ready to implement the design and create a bitstream. Let's click on Generate Bitstream, then click on OK to launch the implementation first. Now that we have a successful run and valid bitstream generated, we can open the Hardware Manager by selecting Open Hardware Manager. Vivado Device Programmer is a part of the Vivado Hardware Manager. Now we'll need to go to the directory where the bitstream was created so that we can go to the Tickle console and type this. This will bring us the directory where the bitstream is generated. So let's confirm this is the right directory. And we can see that the small counter.bit has been created from the design. Now we're ready to create the configuration memory file. Let's type the following command to create an MCS file for the BPI by 16 32 megabit configuration memory. We now have an MCS file for the small counter we can use. Next, let's connect to the board. So we'll go ahead and open a new hardware manager from the green banner on top. And this opens a connection wizard. So let's hit Next. Now confirm that we're connecting directly to the board. That is connected to the machine. So we'll leave the setting at local server and click Next. The XC7K325T part has been recognized on the board, so we can click Next again and finish. Now we need to add a configuration memory device, so we'll right-click on the FPGA and select Add Configuration Memory Device. We know that this board has a 28F00AP30T part, so let's search for it in the search box. In this case, we can enter in 28F00 to narrow down the results, and then select the 28F00AP30T BPI-X16 and click OK. Let's go ahead and program the device now. You have the option to program the device later, although let's go ahead and do that right now. So let's click on OK in this dialog, and we're going to program the configuration memory this time. So let's uncheck the Erase option and the Verify option. The only option selected should be Program. Now we need to point to a configuration file, so let's click here to point to the location of the file. We'll need to go into this project folder in the implementation folder, and now we can see the small counter bpix16.mcs file we had created with the right config mem. So let's select that file and click OK. Now we're ready to program. So let's confirm in the settings that only program is set and the correct MCS file is pointed to, and we can click OK. Now, Vivado Device Programmer is programming the configuration memory on the board with the MCS file we had created earlier. Let's wait for this process to complete. We can see that the programming is successful. Now let's go ahead and verify the configuration memory device. In order to verify the configuration memory device, we'll have to right-click on the configuration memory and select Program Configuration Memory Device again. Now I'll go ahead and uncheck the Program option and check Verify option and click OK. Let's wait for the Verify operation to complete. We can see that we have received a successful verify, so now we're ready to boot the FPGA. Let's go to the FPGA, right-click, and select Boot Device. This will issue a softboot jprogram command so that we can confirm that the FPGA can be booted by the configuration memory. Click on OK to boot the device. We can see that we have successfully booted the FPGA from the configuration memory device, and the Done pin has gone high. With that, we have indirectly programmed an FPGA using a configuration memory device. Let's recap what we've learned today. We've learned how to set correct bitstream properties for your configuration memory. We learned how to generate a configuration memory device file. Then we learned how to take this configuration memory file and program the configuration memory on your board. Finally, we saw how to indirectly program an FPGA with that configuration memory. So please refer to the additional resources to learn more about these capabilities. Please refer specifically to the Setting and Editing Device Properties Quick Take video, as well as the Vivado Design Flows overview for a general understanding of the Vivado flow. There are additional instructor-led training offerings as well if you're interested in learning more. The following user guides go into deeper details on the concepts we covered today and more. Thank you for watching this quick take video on how to indirectly program an FPGA with Vivado Device Programmer.